Do you know what this image is of? If your answer is a blurry space drainage that looks like the eye of Sauron, well, you're not wrong. This is a photo of a black hole. And I know it doesn't look like one from the movies like Interstellar because this is a real picture of a black hole. Also, this thing is in the center of our galaxy. Pretty cool, right? But how did we take a picture of a black hole?
Hey guys, this is AI. So the black hole in this image is called Sagittarius A star. It is a supermassive black hole at the center of our galaxy Milky Way. And it is about 26,000 light years away from Earth and about 4.3 million times the mass of Sun. So in this video, I want to talk about what are you doing?
Oh, shooting a black hole. Look, really. This is a black hole. Everything in the universe can become a black hole if its mass is compressed enough to contain a certain volume, making it extremely dense. This would make its gravitational pull so great that it becomes a black hole. The radius of this new dense shape is called Schwarzschild radius. If we somehow compress the entire Earth to a size that would fit in the palm of your hands, it would create a black hole. If we compress a human being smaller than an atom, we will form a black hole. This seemingly impractical to perform experiment is what actually happens in stars after their lifetime. A star that is huge enough collapses into itself after it can't keep itself burning and succumbs to its own gravity and forms a black hole.
So here I have a phone, the most popular device used to take photographs. But if you want to go a little bit professional, like a DSLR, with the right setup you can take photographs of even the Milky Way. But how do these cameras work?
The way these cameras work is when light passes through the lens, it gets focused on the image sensor. So we are focusing light from an object on the image sensor with lenses. For faraway objects like stars and galaxies, we just need stronger lenses or devices that can focus light from very far away, aka telescopes. We use various telescopes on Earth and even in space to observe light from celestial objects.
But there's one problem. Black holes don't emit light. In fact, the gravitational force of a black hole is so strong that light cannot escape it.
Light can't escape a black hole. So what we're actually seeing in this picture is the hot plasma swirling around it from everything to stars and planets that it has devoured and formed an accretion disk.
Well, I'm doing it. Where are you? I'm going to take a picture of a black hole. Don't worry about me. I'm going to the black hole Sagittarius A star. And from the distance where I'm from it, what we can see is a bright ball of light. It looks like an illusion. This is due to something called gravitational lensing.
Gravitational fields from large objects like stars and black holes tend to bend space-time itself. That is, the four-dimensional fabric combining the three dimensions that we know and time as the fourth dimension. And even light is affected by this. Let's say a star is behind the sun from where we are observing on Earth. This star should be partially visible or not visible at all to us. But due to the sun's gravitational field bending space-time, we observe the star in a totally different location. Let's take a case of a black hole here. As the black hole passes the galaxy behind it, it warps the light coming from the galaxy.
Oh, here we are. This enormous swirling flow of gas and dust, moving at very high speeds, waiting to be eaten by the black hole, is called the accretion disk. It constitutes the most in capturing the image of a black hole because of its bright nature.
Now the accretion disk does not extend all the way to the black hole. There's an innermost stable orbit where matter can orbit without falling in. Well, now because I'm in my room in front of a green screen, I can get out of my spaceship and breathe in space with some editing magic. So let's go further. Going in further, we reach the photon sphere. Here light itself is orbiting around the black hole. So if I look to the side here, I can look at the back of my own head as light is traveling around the black hole and reaching my eyes. Now I'm gonna go into the black hole. Wait, I don't have the budget for that. Okay, now coming back to it. Now you would say, doesn't light travel in a straight line? Well, like I've said before, massive objects warp space-time. So light is still traveling in a straight line, except the path it is taking itself is warped. Here I have the picture. Here the black part in the middle of the image is the event horizon of the black hole. Not to be confused with the movie,
But unlike any object in the sky, like the moon where we see the parts that are facing us, here we see the entirety of the event horizon, even the parts that are not facing us. If light were to reflect from near the event horizon, most of it would never escape the black hole. In fact, light above the event horizon would fall back into the black hole in the backside. It's only the light about 2.6 times black hole's radius would be the light to orbit around the photon sphere and reach us. So if we were to trace this into a flat surface, that's what a picture technically is, we will have a dark patch 2.6 times the black hole's radius, with a ring of light surrounding it. This dark patch contains the entire surface area of the event horizon. But the big issue we actually have while capturing black holes' image is the fact that they are very small in the night sky, just cause they are so far away even though they are massive. If we divide the night sky into degrees in field of view, we can determine objects by degrees of night sky they take up of. If we divide a degree by 60, we get an arc minute, a smaller unit for angle. Furthermore, it can be divided into arc seconds. The black hole at the center of our galaxy takes about 0.0001 arc seconds of the night sky. Pretty small. This black hole was observed using radio waves instead of visible light. So in order to observe the radio waves, we use radio telescopes. To observe something this small, we need a telescope with very small angular resolution. Angular resolution is basically the sensitivity of the telescope. For example, if the radio telescope directly observes the region from which the radio waves from the black hole are coming, it would form an image. Angular resolution is inversely proportional to the diameter of the telescope. But a black hole is so small in the sky that to observe it, we need a telescope as big as the Earth. That seems impossible. But behold the Event Horizon Telescope. This is not one, but several radio telescopes spanned around the Earth. So just by combining the signals from all these telescopes, we can emulate a telescope as big as the Earth and we can achieve the angular resolution required. All these telescopes record the data at an exact time. And this data, which comes in petabytes, is sort of stitched together to form a final result. A pair of these telescopes can observe a fringe pattern, and multiple pairs form multiple patterns. When these patterns are combined, they form the final image as we see now. The seemingly impossible image. The image of a black hole. Human ingenuity. No sign of stopping it.